Alright, so let's look at this integral. Let's say I had the integral of x squared plus 3 over x times the square root of x squared minus 4. Alright, so we would want to see, does this fit any of our integration rules? Now, the first thing that I think of when I see a fraction is this some type of natural log integral? It doesn't appear to be, because the denominator looks pretty complex. If I let the entire denominator be my u, I really don't think that my du is present. I'd have to do a product rule with a u substitution in there, and it would, I mean, there's a chance, but it just doesn't look right. It doesn't look like it would happen. I do see something on the outside of a radical, and I see a square root on the bottom, and we have an x squared minus 4, so that's like a u squared minus a squared, and that would kind of looks like a, you know, if that's u squared, then u is x. The only problem is I have all this extra stuff up here. All this extra stuff is a problem. If I had just a constant up here, so let's pretend that this x squared was gone and I just had a 3, then my u is x, so my du is 1, and it would fit the formula for arcsecant, right, which you should be familiarizing yourself with. The formula for arcsecant is the integral of du over u times the square root of u squared minus a squared. And so it would fit that form if it was just a 3 up here. But it's not just a 3 up here. We have an x squared up here. And so that tells me that I'm probably able to rewrite this using a little algebra, and then maybe go from there. And so if I look at it and I think about algebra, one thing that you can do with fractions with algebra is you can break it up using piecewise division. Meaning, if I have a fraction and I have multiple pieces in my numerator, I can say this first term over the denominator, and then I could say plus the second term over the denominator, and so on and so forth. So one way, and this is just, I'm just trying this way. It may not work. This may not pan out. But I see this problem, and that's the first thing that I start thinking of, because I've practiced so many of these. So if you haven't practiced a lot of these, this is when you get a chance not only to work on your calculus, but work on your algebra. So this is the integral of x squared over x times the square root of x squared minus 4. So you see what I'm doing? I'm taking the first term and putting it over the denominator, plus 3 over x square roots of x squared minus 4. Okay. What I have written here, these two terms, this is the same thing as my original integrand. Okay. So this second integral right here, this second part, this second term in my integrand now, this is what I would need to have an arcsecant integral. So this is for sure an arcsecant integral. We have to figure out what type of integral is this, though. That's the hard part. And if we can't figure out what type of integral this is, then I can't do this using this method, because we have to be able to integrate everything in the problem. Okay? And so the very keen algebra student or very keen math student sees that you have a product of x times this in the denominator and you have an x squared in the numerator. So right away you see that you can cancel this x and one of these x's out, right? And you say, man, I hope that simplifies things so that I can do this first integral because, or the first part of the integral, because I know I can do the second part. So let's see if that simplified things. Okay, so look at this first part here. This isn't a natural log integral because I can't take the entire denominator and make that my u. But what if I was just to take what's under the radical and make that my u? Just what's under the radical. And this is just for this the integral of this first term here. So then what would my du be? 2x. And look, this x is present in the numerator, like it would have to be for a u substitution. Now, this isn't 1 over u. This isn't 1 over u. This is 1 over the square root of u. Okay? So if I treat this like it's 1 over the square root of u, because I have my du present, I need to bring out a 1/2, right? So that's going to give me 1/2 times the integral of 1 over the square root of u du. Okay? Now, that's just the integral of this first term. I haven't done the integral of the second part of the integrand. But I need to go ahead and, I'm going to go ahead and do this integral. Okay? So that's equal to 1/2 times the integral of u to the negative 1/2. Alright, which is 1/2. Now add 1 to the power, it will become u to the 1/2. Divide by that power, so you're multiplying by 2 over 1, or if you divide by 1/2, those cancel out. Okay, and so all I have to do is plug my u back in. So I've worked out the first part of this integral. It is simply x squared minus 4 to the 1/2 power, or you could say the square root of x squared minus 4. Alright, let's work out the second part, which we figured out earlier. Alright, the second part is an arcsecant integral. How do I know that? Because I have a u squared here, where my u would be equal to x, and that u is right there. And I have an a squared there, so a would be equal to 2. And I have a minus sign here, which is very important, because my formula for arcsecant has a minus sign there. And then if my u in my formula is x, my du is 1. And I have a constant in the numerator, so that 1, that's okay to have a constant there. If there was a variable up there, this would not be an arcsecant integral. Alright, so let's work on this integral now. So this is plus. Now bring out any constants first. So bring out a 3. And now we follow our formula for arcsecant. And our formula for arcsecant is 1 over a, so times 1 over 2, arcsecant. Remember, that's the same as inverse secant, of the absolute value of u over a. So the absolute value of, what was my u? X over 2. plus c. All right, so I'm going to go down here where I have my first part of my answer. This is 3 over 2 arcsecant absolute value of x over 2 plus c. Let's think a second about the form that we need an integral in for arctangent. It's 1 over u squared plus a squared, or a squared plus u squared du. And so the variable part is your u squared, the a squared is your constant. So you could have a quadratic in a denominator, and if we have a quadratic in a denominator, we could factor that quadratic by completing the square, you know, and get it in the form that would allow us to find the integral. So for example, if you ever see the integral of 1 over a quadratic, it's not going to factor more than likely. It may not, but we don't want it just to factor as far as like one linear factor times another linear factor. What we want, if it did that, it's something called partial fractions, which we'll go over in a few chapters. But if we have a quadratic here, and we can complete the square, which all completing the square does really is rewrite a quadratic into a different form, then it will be in the form u squared plus a squared. So let me show you what I'm talking about. So let's just take this integrand and see what we would have to do to complete the square. All right. In algebra, when you're taught to complete the square, you're doing it to solve an equation. But we're not solving an equation here. We're not solving for x. So the reason I'm saying this is, when you learn this early on in math, you have it set equal to 0 usually. And so you're taught, take the constant and move it over, put plus blank, and then what you do to one side you have to do the other. We don't have sides here. This is all together. So whenever I complete this square, what you have to do, we don't move the constant over like we would in an equation. So whatever I put in this blank here, I have to also subtract here. So if I'm going to add something, which you always have plus blank here after your x term, whatever you add here to make this where it'll factor, you have to subtract. Because if we add something and subtract something, we're not really doing anything as far as we're not throwing the balance out on the whole quadratic. It's the same quadratic. So the way that you figure out what to put in this blank is you take the number in front of x, you take half of it and square it. So half of 4 is 2, 2 squared is 4. Half of the number in front of x and square it. Don't worry about the positive or negative sign in front of the x yet. So if I add 4 here, I need to subtract 4 here. That makes sure that we can't just add numbers to equations when we want to, or to parts of an expression when we want to. If we add something, we have to subtract that same something. All right, the reason for doing that, the reason why we complete the square, is so this will factor. This becomes a perfect square. Okay? This becomes Put x, x. Whatever the sign is right here, you put here and here. So minus, minus. And then the number you got when you took half of this goes here and here. 2, 2. So x squared minus 4x plus 4 is x minus 2 times x minus 2. Or x minus 2 squared. Then a plus 7 and a minus 4, that's going to be plus 3. So if you were to square x minus 2 and add 3 to it, you would get x squared minus 4x plus 7. So all we've done is we've applied an algebra trick called completing the square, and now we've rewritten this, which rewrites my integrand in a way that I have 1 over u squared plus a squared. And so now that my integrand is in that form, you do have to make sure that you write down what your u is equal to. Your u is going to be x minus 2, so your du would have to be 1. You do have to check and make sure that your du is present, so it's just a constant, so that's okay. But other than that, there's nothing really to check. It's just it's a arctangent integral now. So adjust for the constant, which there's nothing to adjust for. There's nothing to factor out here. So I can start applying my arctangent formula. Alright, so that's going to be what? 1 over a. What is a? A squared is 3. So a is the square root of 3. So 1 over the square root of 3. Arctangent u over a. So u is x minus 2. A is square root of 3 plus c. It is acceptable to leave your answer in this form, but me personally, I rationalize. Even though it does make this part look a little, I guess this part does get a little more complicated, but I usually rationalize.